it's one of the sort of prominent applications of analytic combinatorics to attack questions in analytic number theory. Um, Specifically the type of analytic number theory in which you're concerned with questions regarding the distribution of primes or things related to primes, like the Mobius function and so forth. Um, yeah, so the way I like to think about this subject, like with many other fields of mathematics, it's kind of a battleground between structure and randomness. The primes seem to be somewhat a combination of both of both phenomena. Uh, so um, okay, so just to give you an example, all right, so I think number theory is an area where we sort of know what's true and what's not to a really high degree, but we can prove only a very small fraction of what we can conjecture. It's rather annoying the equation. So for example, we have this infamous twin prime conjecture, which is at least 300 years old. Infinitely many pairs of primes p plus 2, and we are like 99.9% certain it's true. And we can even I can tell you the prediction how many primes there are, twin primes there are after number x, but we can't prove. We can do partial results. So, for example, thanks to the work of Yitang Zhang and then James Maynard and the Polymath project, we know, for example, there's infinitely many pairs of primes that are not distance 2 apart, but distance somewhere between 2 and 246. And this conjecture is part of a more general prime tuples conjecture that if you replace p plus 2 by a more general tuple p plus h1 up to p plus hk, we have a very precise prediction for how many tuples of this type we should see. Okay, so but we are very confident this is true because yeah. So we have a heuristic model for what's going on. Okay, so first of all, we have a theorem. Okay, we have the prime number theorem. The number of primes up to a large number x is basically x over log x, or more precisely, the integral of 1 over log b. So informally, you pick a random number n, large number n, the probability that it's prime is like 1 over log n. The nice thing you can do is what's called the Cramer random model. You just pick a random set of this density. So you can formally take a Poisson process where every natural number has an independent chance of 1 over log n of being prime. And if you just naively took that model, you would make a prediction that the number of twin primes up to x should be roughly the integral of 1 over log squared, which is roughly x over log squared x. So that's what would happen if the primes were completely random. Now, primes are not completely random because they do have biases. For example, they're almost completely situated in the odd numbers and not in the even numbers. So saying that every number has a 1 in log n chance of being prime is inaccurate. A better model would be to say that any large even number has a 0 probability of being prime, and every odd number would have a 2 over log n chance of being prime to compensate. So that's a slightly better model. And then you can also throw in the prime 3. So now a slightly refined model is that any number which is divisible by 2 or 3 has a 0 chance of being prime. And the numbers that are co-prime 2 and 3 would have probably, I think, 3 over log n of being prime. And so you can create this little, so that's what you might call the Cramer-Granville model at level 3, or level 2, level 3, and then you can slowly increase this level to something maybe like log x or something. And if you do that, you adjust the prediction. And if you do the calculations, the number of twin primes with the Cramer-Granville random model is the naive random prediction with an arithmetic correction coming from the irregularities at small primes. So the prime 2, the fact that all the primes concentrate in odd numbers, that basically doubles the count of expected count of twin primes. And so you get a factor of 2 here. And then all the other primes, the odd primes, slightly decrease the expected number of twin primes because if you exclude the multiple of 3, if you force the primes to co-prime to 3, once p is co-prime to 3, that actually elevates the chance that p plus 2 is divisible by 3 a little bit. So you have to make a slight correction, but it's a convergent correction. Each prime corrects things less and less. And so the actual prediction is the integral of log squared times a number called the twin prime constant, 1.32 something. Okay, so this is the prediction. And numerically, that's extremely accurate. Okay, so like if you count, for example, how many twin primes there are up to 10 to the 15, it's 1.1 times 10 to the 14 or something. But yeah, you can see that this prediction that I just wrote down is quite accurate. what this numeric evidence is telling you somehow is that the naive structure that you see in the primes, that it's copriming to 2, copriming to 3, and so forth, that's kind of the only visible structure that should actually influence the statistics of questions like the twin primes. And numerically, we're not detecting any other pattern in the twin primes beyond the obvious things. But that's not a proof. So the problem is that there could be other weird structure in the primes, conspiracies between the primes, which maybe past the limit of numerical data would start influencing this count. We don't have that. We can't include that much to our annoyance.
So it's about half the digits. So it's like
Yes,
square root.
it is like square root. Yes. Okay. So there's the strong Heidelberg Cooper's conjecture, which is that the error in these predictions is always square root size, and we up to maybe epsilon exponent. And yeah, we pretty much believe that conjecture. Yeah. So that's a very strong affirmation that the structure that you see that I've just noted is the only structure that is out. Yeah, so every time we do statistics, our random models are pretty much in complete agreement, up to the expected square root error. Yeah, there've been a few occasions where we've been slightly surprised. Like there were some biases in the in consecutive gaps between primes and so forth. But we have also, but that was just because we didn't run the model correctly. Okay, those have been explained too. All right. Yeah, so we can't solve the twin prime conjecture, much as we would love to. I would love to. But in many cases, yeah, once your pattern has a finite complexity, we can use additive combinatorics to deal with the fact that we don't fully understand the how random the primes are. So there are sort of two basic ways you can do this. One is that there are some additive combinatorics results which have the great advantage that they work for all sets of a certain size. The most famous example is Zermeri's theorem. That if you have a set of positive density, then it has arithmetic progressions, and it doesn't matter what set, how random or how structured the set is, it will always have arithmetic progressions. And so the reason why Zermeri's theorem is so useful is that it doesn't require you to know very much about the set, just its size. And size, at least, is one thing we do know about the primes. Yeah, so if you're lucky enough to have an additive combinatorics result that works for all sets of a certain size, then that's a sort of fairly obvious way to use additive combinatorics. Now, you're not always so lucky as to be in that situation. So then you have to work harder. But then additive combinatorics has this other set of tools, these inverse theorems, that sometimes they can tell you that usually, if you're going to count the number of patterns of a certain size, usually you'll get this number, unless your set has a certain very specific structure. And then that identifies the very specific unusual cases in which the primes or whatever set you're studying do not have the behavior you expect. And then if you can apply some other technique, maybe from analytic number theory, to say the primes are not behaving in this one particular structured scenario, then they must be in the random scenario. So that is a slightly more sophisticated way to use additive combinatorics to rule out or to sort of explain the cases in which sort of the prediction can fail. Yeah, that works when your pattern has finite complexity. The problem with the twin prime conjecture is that it has infinite complexity. There are like way too many ways in which the twin prime conjecture can fail. But for things like arithmetic progressions, there are many, many fewer ways that the random prediction can fail. Okay, so really, really simple example, except it's also simple, but also conditional, because this doesn't work yet to improve the conjecture. Yeah, so for example, suppose you want to prove that the primes contain arbitrarily long arithmetic progressions. So the initial strategy to do this was proposed by Erdős is, why don't we forget about primes and just prove an additive combinatorics conjecture, which is an infamous conjecture, number 3 on Thomas Bloom's website. That if a set of numbers whose sum of reciprocals diverges, then it should contain arbitrarily long arithmetic progressions. So that is still open. We now know that it contains progressions of length 3, but we don't know the arbitrary long case. But if you have this as an immediate corollary, the primes would contain arbitrary long arithmetic progressions, because it was proved by Euler way back when that the sum of reciprocals of primes diverges, and that's like a 6-line proof. Okay, but So this would be the textbook way example of how additive combinatorics could be used to solve a problem in analytic number theory, except that we haven't proved this conjecture. Nevertheless, we can prove that the primes do contain average long arithmetic progressions. Ben Green and I did that back in 2008 or 2004, published 2008. But using a slightly more sophisticated additive combinatoric strategy, which I'll talk about later. Yeah. Meanwhile, we are making progress on this conjecture. Okay, so so it's solved for the three progressions thanks to Bloom, Cisak, and then Kili-Meca, and the bounds are getting better in length 4 and length 5. So as you saw with the papers made up James. Okay, but that's sort of the famous example. Here's another classic example. So there's this number called Schnurmann's constant historically. It's the least number C such that every number bigger than 1 is the sum of most C primes. Okay, so how many primes, to what extent are the primes added to basis of the natural numbers? So how many primes do you need to generate all the natural numbers? Yeah, so the conjecture is 3, right? And that's basically the even Goldbach conjecture. Even Goldbach says that every even number bigger than 4 is the sum of 2 primes, and therefore every odd number bigger than 7 is the sum of 3 primes. Yeah, so and it's not quite equivalent, but it's really close to being equivalent. Yeah, so the conjecture is 3. Yeah, so long time ago, Schnurman proved that it's at least finite. Okay, using additive combinatorics and quite inefficient argument. So its value for C was like 800,000 eventually. There was a very nice argument of Ramiret in 95 that got C down to something civilized, 7. Current record is 4, basically because Harold solved the odd Goldbach conjecture. And there were many intermediate results, including one of my own, which I'm not going to mention here. Okay. Yeah, but I wanted to discuss Ramiret's approach. Yeah. So okay, so he used just a tiny bit of number theory and mostly additive combinatorics and sort of Cauchy-Schwarz type things, which right. So the primes themselves are fairly sparse. Okay, the primes after X is only X over log X primes, so that's a zero density set. But even just after taking one subset, primes plus primes, you get a much bigger set because if you count how many primes, okay, if you want to sum 2 primes up to X, there are about X squared over log squared X ways to express a number sum of 2 primes. But of course, there are collisions. Okay, a single number can be represented in many ways as a sum of 2 primes. But even though we can't solve things like the Trim-Hack conjecture or the Goldbach conjecture, we have the tool of sieve theory, and sieve theory lets you get upper bounds on how many times, how many primes do certain things. So while we can't actually count how many ways a number is sum of 2 primes exactly, we can upper bound them pretty well. And the random prediction, if it was a random set, the number of ways you could represent a number size X, sum of 2 primes, should be about X over log squared X because of the density of 1 over log X. And that turns out to basically be the truth. For a typical number, the number of representations is of size X over log squared X. There's a slight caveat. If your number that you're representing is divisible by many, many small primes, it actually slightly elevates the probability of being a number of representations. So you lose a little bit, but on average, this is true. So just from that and Schwartz or something or Holder, that tells you if there's X squared log squared pairs of sums of 2 primes, and each number can be represented in at most X over log squared X, then just from Holder, yeah, then the number of numbers that are sum of 2 primes has a positive density, has a bigger than constant X. Okay, so just by taking the sum of 2, you get positive density. And in fact, Ramiret actually by refining this argument, basically it's computing added energy of the primes. That's the bottom. But you got an explicit positive density like 1/3 or something like that. And then you just apply another additive combinatorics tool. I think the Mann inequality in this case, that under certain conditions you can lower bound the density. A subset, you have 2 subsets, 2 infinite sets A and B of a certain density. The subset will have even larger density. Yeah, so if A is density alpha and B is density beta, then under certain hypotheses, A plus B will have density alpha plus beta. Yeah, for certain notions of density. And so Just by applying things like that, you can get this positive density. You add this to yourself a couple more times, and Raman was able to show that the 7 for some set was already of the whole thing. Okay. Yeah, but these are the basic ingredients. Yeah, so you're not using too much about the primes. You're basically letting additive combinatorics do most of the work. All right. All right. So yeah, so the thing about the primes is that we really don't know much about them. I mean, they're a deterministic set, I mean, we have a definition, but their additive structure in particular, it's very mysterious. I mean, the multiplicative structure we understand reasonably well, although even there we have the Riemann hypothesis, right, which we don't understand, but we have a pretty good understanding of the multiplicative structure, but it's the additive structure which is slippery. So I'm going to show you a sequence of pictures, which is sort of the way I think about how the primes look. So in this picture, you pick a large number x and you take some big interval like x2x. Okay, so I think I'm going to represent about this big square. Okay, so the space of numbers from x to 2x is this square. And the primes is just some mysterious set inside this square. The primes inside x to 2x. And to begin with, all we know is the density. Okay, so the prime number theorem tells you how big it is. It has density 1 over log x, so moderately dense. We don't know how it's distributed, so it's just some messy looking set in this square. Okay, but it could be anything, density, a priori. Okay, but we do know some things about the primes that start constraining its behavior. So, for example, we can partition the numbers from x to 2x into the odd numbers and the even numbers. And I'm going to represent them by these big rectangles here, of size 1/2 each. Okay, and the primes will only live in the odd numbers. Okay, so that already gives us more information about the prime numbers. So rather than being sort of an arbitrary set of density 1 over log x in the big square, it's actually squished into this bottom rectangle, and the primes actually look like a set of density 2 over log x in this rectangle of half the size of the original set. Okay, so that's telling you more information about the primes, but still not that much because there are a lot of sets of density 2 over log x in the class. Okay, but of course you can keep going. If you sieve out 3 as well, then now the set of numbers that are coprime to both 2 and 3 turns out to be represented by a rectangle of size 1/3 inside the whole rectangle. And so now the relative density is a bit thicker. It's now 3 over log x. Okay, so you're filling out a bit more of this box. Yeah. So the sort of what I'm trying to depict with these pictures is that sets with a very simple boundary, like rectangles, these are sets that we understand very well. Okay? And sets with very irregular boundaries, these depict sets that we do not understand very well. So we still don't understand the primes, but at least we're containing them more and more efficiently inside sets that we do understand. Okay, now of course you can keep iterating this with about 5 and 7 and so forth. Okay, and so we have this whole science of sieve theory, number theory, which is designed to push this to the limit. And so roughly speaking, you can sieve out multiples of 2, 3, 5, up to a small power of x, like x to the 1/10. And if you want to summarize 100 years of sieve theory in one sentence, the summary is that you can sieve up to that level of x to the 1/10, and your set still deserves to be shaped like a rectangle. It's a set that we still understand what it looks like. We can count how many elements there are. We can count how many twins there are inside it. We understand the statistics. So you can sieve out all numbers which have a prime factor less than x to the 1/10. And what's left are the almost primes, the numbers whose only prime factors are bigger than x 1/10. In particular, there's only like 10 prime factors at most. So an almost prime, this is a slightly fuzzy concept. What almost prime means precisely depends on your precise application. But think of an almost prime as a number which is either prime or only has a few prime factors, a few large prime factors, not divisible by small primes. So maybe a semi-prime, product of 2 primes or maybe primes. But I'm still going to depict it by a rectangle, saying that we understand it pretty well. And then by the time you get to this almost primes, the relative density has been increasing. So the primes themselves sit inside the almost primes, but now the relative density is actually a constant. If you sieve out up to x to the 1/10, the relative density is roughly about 1/10. Yeah, unfortunately, sieve theory starts hitting limits around this time. There's a really serious problem sieving up to x to the 1/2. This is really what's called the parity problem. But even before 1/2, the wheels start falling off sieve theory. and you less. I mean, I, some of the rectangles should become more and more jagged and blurry. Yeah, of course, if you can sieve up to root x, then the simple Eratosthenes would tell you that you get exactly the primes. But sieve theory encounters limitations before that. Okay, so this is a model of the primes. So this already tells you a lot. So I told you, for example, this upper bound. Like if you want to count how many ways you can represent a number sum of two primes, I said it was big O of x over log squared x. And one way you can prove it is that you just count how many ways you can represent a number sum of two almost primes. And that turns out to also be big O of x over log squared x. And because the primes are containing the almost primes, that gives you the upper bound. And we can do that because the almost primes are a set that we understand. I mean, it's like the set of odd numbers is a set we understand. You want to count twins of the odd numbers. This is very easy. Or represent the numbers of sum two odd numbers, or the numbers co-prime to 2 and 3. Again, it's not too hard to count how many numbers how many ways you can represent a number sum of two numbers that co-prime to 2 and 3 and so forth. So you can believe that if you're just careful enough, you can understand almost primes. But somehow the only thing left is to understand this density one gap. Okay, that this is a set we understand, the almost primes, and then we have this set that we don't understand, but at least it's now just a positive density fraction rather than a tiny density fraction of the set that we do understand. Okay. Now, this set is, in addition to being containing the almost primes, there are other things that we do understand about it. These primes do behave in a fairly, okay, so yeah, they are biased with respect to 2 and 3 and 5, okay, but we have the standard trick called the W trick that just gets rid of them. So you can restrict to a single residue class. Like if you want to ignore the fact that primes are odd, you just restrict attention to 1 mod 2, the numbers 1 mod 2, and then you have sort of incorporated the information that primes are co-prime to 2. If you want to ignore the fact that primes are co-prime to 3, you can restrict attention to numbers that say 1 mod 6. And now you've automatically incorporated the information that you are co-prime to 3. So what we often do, especially if we don't care so much about quantitative bounds, is that we just restrict attention to a single residue class B mod W, where W is the product of small primes, like 1 mod 6 or 1 mod 24 or whatever. And then that gets rid of all the obvious irregularities of the primes. And what we expect remains is sort of a random looking set. And this Cramer-Granville model that I mentioned is basically a slightly more rigorous instantiation of that assertion. And one way you can actually quantify the randomness of the primes is to say that it's not correlated with various structured sets. So in this picture, yeah, the horizontal rectangles are going to depict sort of sets that come from sieve theory, and these are sets that we understand from sieve theoretic reasons. I've also got these vertical rectangles, and these are the structured sets that show up in additive combinatorics. So a standard example is a Bohr set. If you pick an interval I and some real number alpha, say root 2, a Bohr set is just all the numbers whose exponential of n alpha lies in that interval I, or if you like, all fractional parts of n alpha. I think I is an arc on the circle, the way I've written it here. Okay, so like maybe set of all numbers where the fractional part of root 2n is less than 0.1. That's a set of size 1/10 inside this block. So I think of it as a vertical rectangle. It's kind of orthogonal to the sieve theoretic rectangles, especially the alpha's major arc, minor arc. So yeah, but what you can show is that actually the primes are not correlated with these Bohr sets. So the size of the intersection of this set and this set is roughly the product of the densities. Yeah, that's because we're able to understand, we're able to compute reasonable accuracy exponential sums like this. Okay, so Vinogradov taught us how to do sums like this, and these sums are basically telling us how to control correlation between primes and like Bohr sets. And then you can do more complicated things. You can put like an n squared alpha here. Then you'd have to deal with slightly more complicated exponential sums over here. But we also know how to control these guys. Yeah, but the upshot is that any structured set, by which I mean like a vertical rectangle, is kind of is orthogonal or uncorrelated with a set like this. All right. So that's another thing we do know about primes. Okay, now the other thing we have is that we have this very useful transference principle, which was sort of by Ben, and then I developed it further with Ben and later work with Thomas Ziegler and then Conrad Foch-Zau and so forth. Yeah, so these sets, so the primes they are not dense in the whole space. They have density 0 or 1 over log x in the whole space, but they have positive density inside these almost primes. But the almost primes have this additional property that they're pseudo-random, that they're very, very uncorrelated with structured sets, structured objects. So yeah, that's why I draw them as horizontal rectangles, because those are uncorrelated with vertical rectangles. So because of that, even though your set doesn't have positive density in the whole space, you can there's a proxy. You can approximate it in some sense by a positive density, well, not a set, but a function actually in the whole space. So uh, um, so there exists a structured function which yeah, in this picture, structured function, you should think of it as like a function which is constant on vertical lines. So yeah, I drew it as a hidden box. Some lines are denser than others, and that you can kind of project this sort of a normalized indicator function on the primes actually onto the structured part. So you just kind of averaging out on vertical lines, and then that will smear out this set of primes into a structured object. And so we have these structure theorems or transference principles that tell you that every that any function of say any bounded function on say on a pseudo-random set such as the almost primes can be approximated by a structured function on which is now so, positive density on the whole space plus an error which is very pseudo-random. Which is orthogonal to all structured functions, and therefore has things like small Gauss norm contribute to progressions and things like that. So you can approximate this very sparse set suitably normalized by a very by a positive density set. So that's a very useful principle. Yeah, so so the primes sort of morally have positive density, or they have a proxy in the whole natural numbers that have positive density. Yeah, so if you want to make this precise, what you do is that you take the Mangold function, which is a normalized indicator function of the primes. You apply the W trick to remove small irregularities. So you restrict to a raised to class B mod W for some reason small W. Restricting this class elevates the chance of being prime, so you have to renormalize by the Euler W or W. But this function can be decomposed into a structured function, which is bounded and has the same mean one. So it's a proxy for the primes, and then there's an error which you can make small in various norms, like the Gauss equal norms. So Ben was the first to do decomposition like this. He was using Fourier analysis and using sort of Fourier analytic properties of the primes, and so the error was controlled initially first only in a Fourier sense, and then with Ben we upgrade the error to be small in higher Fourier norms, Gauss norms as well. Our proof was quite complicated. It was based on trying to quantify and make finite an ergodic theory argument, which is very simple in ergodic theory, just a conditional expectation to a sigma algebra. But you can't, but we had to work with finite sigma algebras and the discretize them and so forth. And it was kind of annoying. Okay, they're now very clean proofs of so it was later observed by Gauss and Reingold, Trevisan, Tosian, and Baran that easily get this from the Hahn-Banach theorem actually. And then we needed quite a few restrictions on how pseudo-random these almost primes were, but these have since been relaxed. So there's the modern proof. So Conlon, Fox, and Zhao had this very nice alternate way to do this using the method of densification, which gives a much gives a stronger and cleaner proof of this type of structure theory. Okay, but that's all I'll say about that. Yeah, so that principle, so morally you can explain a lot of recent results in the or more relatively recent results in this literature. So morally speaking, for example, as I said, Ben and I, we proved that the primes contain arbitrary long arithmetic progression, and once you have the transference principle in hand, and you have enough sieve theory to know that the almost primes are pseudo-random, this morally is a corollary of Zermani's theorem. Zermani's theorem says that any positive density set contains arbitrary long progressions. You can't directly apply Zermani's theorem to our theorem because the primes have zero density, but because of the structure theorem, the transference principle, the von Mangold version of the primes with the W trick can be approximated by, in a Gauss norm sense, by a bounded function of positive density. Zermani tells you that bounded function produces lots of progressions. The error term with small Gauss norm, again, you do a finite amount of Cauchy-Schwarz. You can show that that term does not contribute that many, doesn't change the count of progressions too much, and then you can prove that the primes can start progressions. So that's sort of our paper in a nutshell. Yeah, in a similar spirit, but this is cheating a lot. So Zhang's famous theorem that the primes contain bounded gaps infinitely often. Yeah, so that's morally in the same spirit coming from the Pigeonhole principle that a set of positive density contains arbitrary bounded gaps infinitely often. That's an obvious application of the Pigeonhole principle. Again, this does not directly imply Zhang's theorem because the primes do not have positive density. But relative to a very well chosen measure of representing almost primes, the primes do have positive density. Now, you can't quite transfer the same way we transfer. Yeah, this measure is not translation invariant by any means. But yeah, you can make it translation invariant enough. This argument actually does work. But yeah, then you need a much more delicate sieve theory.
And that's in Goldstone pencil dream. I mean, what Zhang added was something else.
Yeah. Yeah. So Zhang was able to make the sieve theory good enough. Yeah. So Goldstone pencil could make this implication work, but they needed something called the Elliott-Halberstam conjecture. They could almost do it, and they had a sieve that worked up to level x or x squared half, and that gave not quite bounded gaps but smallish gaps. And they needed a sieve theoretic statement that went just a little bit above this x squared half barrier. So they had to break what's called the Bombrier-Vennegout square root barrier, and Zhang was able to do that with a lot of work and get his first bound. Later, Maynard realized that you could, if you be smarter about the sieve, you can even just keep the sieve level at x1/2 and still get this result by using a smarter version of the Silberg sieve, which we now call the Maynard sieve. Okay, all right. But so this is oversimplifying the story, but hopefully the essence it's. Okay, here's another example of the same sort of philosophy. Fernando Shao proved a density version of the Goldbach of the Vinogradov theorem. So Vinogradov proved that every large odd number is a sum of 3 primes. I mean, I know that in fact that every odd number bigger than 7 is the sum of 3 primes. But you can ask, what about if you don't take all the primes, but some subset of the primes? Now, if you take if you don't take enough primes, then you can't do it. Like if you take only the primes at 1.5, then not every number is going to be the sum of 3 primes. But what Fernando showed is that if you take a subset of primes of density at least 5/8, then every odd number is the sum of 3 numbers from that subset of the primes. And 5/8 is optimal. I figured exactly what the presumably you pick some residue classes 1/8, presumably. Or what 6 or 24.
15, wasn't it?
That's not the hard part to work out that 5/8 is sharp. Okay, but yeah, there was some finite sort of residue classes that you can pick to make an example to show that 5/8 can't be proved, but he got the threshold 5/8. And basically, using the transference principle, he reduced it to an added combinatorics result that has nothing to do with the primes. So it basically came from this purely added combinatorial statement that if instead of the primes, it does a subset of the primes, you take a subset of the primitive elements of a cyclic group. So you take Z mod MZ for some M, say square free. You only look at the numbers that are so the X means that you only look at the invertible elements of the cyclic group. If you have a subset of the invertible elements that has density at least 5/8 in that invertible group, then the triple subset goes out the whole space. So that is an added combinatorial result. It's not super difficult. I think you can reduce the case of prime powers in the Cauchy-Davenport type thing. But yeah, that's the main engine used with this. Okay, and so roughly speaking, yeah, you can use the W trig and transference, and basically you can model the set of positive relative density here by either a set or a function that is living inside of it. But the added combinatorics is the main engine once you have this. Okay. Right. So this transference principle combines very well with inverse theorems. So we've seen a lot of inverse theorems already in this workshop. Inverse theorems tell you when certain averages are not what you expect them to be. So a standard average, for example, are these Gauss uniformity norms. So here, for example, is the U2 norm. It's an average of sort of 4 copies of F along these sort of parallelograms. If you take a random F, which is a bounded, you would get something close to 0 here. There'd be loss of cancellation. But occasionally, there are some F for which this average doesn't cancel. In particular, for this particular average, linear averages don't cancel because we have an identity. E alpha n, E minus alpha n plus h, minus n plus k, E alpha plus h plus k. All these phases, they individually oscillate, but collectively they cancel. Basically, because what you're doing here is you're taking a second discrete derivative of alpha n. Alpha n is linear, so its second derivative vanishes. And so this is in this particular case of this if f is a linear phase, then this Gauss norm is 1. There's no cancellation. So more generally, saying this Gauss norm is large is kind of saying that the phase of f, in some statistical sense, has a small second derivative. And if it had a vanishing second derivative, then it have to be linear. But we have this inverse theorem that says that if you have sort of a statistically small second derivative, then you must at least correlate with a linear function. That if this Gauss norm is large, then this function has some large correlation with this phase. Okay, and in fact, the bounds are polynomial. If this bound is bigger than delta, your correlation is like delta squared or something. Okay. So this is a typical example of inverse theorem. This particular one is easy to prove by Fourier analysis. There's a Plancherot identity. Yeah, there are higher order Gauss norms where you take more and more derivatives here, and then you have to take a higher order phase functions here, quadratic phases, no sequences, and so forth. Okay, but we've had talks about that. So yeah, so these combine very well. These inverse theorems, initially they basically mostly restricted to bounded functions, or maybe L2 functions or something. Whereas these more mangled functions are not bounded. So you can't directly apply these inverse theorems to the primes immediately. But because of the transference principle, because you can approximate, say, the more mangled function after a W-trig by a bounded function, you can combine the inverse theorem with the transference principle. And roughly speaking, what that means is that the inverse theorem also applies to things like the primes directly, which is great because yeah, so that lets you prove Gauss uniformity bound. So, for example, here is the W-trig version of the mangled function. You normalize it to have mean 0. One can show that using route of the method of bilinear sums, which is a fancy way of saying loss and loss of Cauchy-Schwarz, that these functions are actually not correlated with any linear phase. Whether alpha is either major arc or minor arc doesn't matter. Actually, they're all small, and because of that, and the inverse theorem and the transference principle, that means that this quantity is small in, say, U2. And then we also know that we can put in other things in place of this linear phase. You can put quadratic phases and no sequences, and these functions are actually small in every Gauss norm, which is great because then you can use this to count because Gauss norms, as we know, because of more Cauchy-Schwarz, controls all these other patterns. So you can start getting asymptotics for all these other things. So going back to my previous picture, yeah, so because of this extra uniformity that we have, the picture that we have of the primes actually looks more like this. Okay, so this is very similar to the previous picture, but the almost primes. So the primes have positive density inside the almost primes, but we actually know that they're kind of equidistributed with respect to structured functions. That the indicator function of the primes is not correlated with any structured function with any vertical rectangle. So that's kind of like saying that if you that every vertical line intersects this set in sort of the same measure. That's sort of the analogy is getting a bit stretched, but that's sort of roughly. So this is how I think of what the primes are looking like. Yeah. So we still don't quite know everything about the primes because like how the set of positive measures sits inside this set is still a little bit mysterious, but this still gives a lot of information. In particular, the structured proxy for this function is actually just a constant function of 1. At least as long as you're inside a single residue class B mod W. So there's a third dimension with the residue class mod W. Again, this is really a delicate picture, but I don't want to. Yeah. this is the Archimedean direction. This is the large prime direction, and there's a small prime direction. But okay, it probably doesn't help you. So okay, okay, yeah, just look at this rectangle. Okay, um, okay, yeah. So that gives you more information. So this tells you actually, roughly speaking, what this tells you is that the Cramer-Granville predictions or the Hardy-Leurer predictions for what primes do is actually well, as long as you have a pattern that is controllable by the Galois norms, and these are what we call finite complexity patterns. So for instance, the progression of length k in the primes is a finite complexity pattern. And so yeah, we actually have a precise count. So just like there's this twin prime constant, there's a more complicated constant counting progression of length k times n log the kn plus a little o. And we can count how many primes there are here. And recently there's been a lot of progress on understanding the error term. I think gain arbitrary as a log a. Log in the error. You have to replace this by an integral or something, but yeah, this is not the latest result. Okay. A couple other examples of how the contourx input gets used. So here's a result of myself and Yoni. People care a lot about patterns of the Liouville function. Here we are looking at it. So the Liouville function counts whether the number of prime factors of a number are even or odd. So you're looking at the number of prime factors mod 2. You can also count prime factors mod 3. And so that's basically a 3 coloring of the natural numbers, depending on whether your number of prime factors is 1 mod 3, 2 mod 3, or 0 mod 3. This is not the theorem that I wanted to. Okay, I think this is n plus I. Yeah, okay. So what this question, what we're trying to study here is color patterns of 3 consecutive numbers. You take n plus 1, n plus 2. So each of them has a color depending on how many prime factors n plus 1, n plus 2 have mod 3. So this n sub I should be n plus I as a typo. And so conjecturally, those 3 colorings are independent. So there are 27 different color patterns for 3 consecutive numbers, and they should each occur density 1 over 27. This we can't prove, but we can prove that they each occur positive density. This relies on transference and some ergodic theory and lots of other things, but the ultimate input is actually an added combinatoric statement. It's an inverse theorem for the Canesian inequality. Yeah. So if you have 2 subsets of a compact connected abelian group that go torus, A and B, the measure of A plus B, I suppose the measure of A and the measure of B is sum to less than 1, then there's an old inequality of for the torus, I think it's McBeef, but in general it's Kneser, I think, that this measure of A plus B is at least the measure of A, this measure of B. But occasionally it's equality. And there is a natural example of its equality. So if you can project your group onto a circle and you pick 2 arcs on that circle, and you pull back the arcs back onto the group, so take the inverse image of 2 arcs on the group, then you can check that in that case, the measure of the sum is the sum of the measures. But that turns out to be the only case, the only way in which this equality can be sharp up to null sets. So I proved that a few years back. There's now a couple of proofs. Actually, technically, this is not enough. You need a stability version. Like suppose you're with an epsilon. Suppose you're with an epsilon equality, then you or with an epsilon, a delta of this example. But yeah, I won't explain why, but this is the main input needed to prove this. Okay, so last thing I'll close with is a very nice work of Rademacher, Merkowski, and Tervainen, of a classical theorem of Linux, which is considered like it's considered like one of the most difficult standard theorems of analytic number theory. Like it's you could barely cover it in a graduate analytic number theory class because it sort of the standard proofs uses like everything that you teach in such a class. So you may know of Dirichlet's theorem for primes and arithmetic progressions. Okay, so if you take a primitive vector class A mod Q, Dirichlet tells you there's infinitely many primes. Right? So there's infinitely many primes, which I say 7, 1, 10. Infinitely many primes other than 7. But the standard proof of Dirichlet's theorem gives you lousy bounds on like so it tells you that there's at least 1 prime in the class A mod Q, but it doesn't tell you where the first prime appears. And if you actually work through the proof, the bounds are terrible. They're exponential in Q. If you have the generalized Riemann hypothesis, then they're polynomial in Q, but we don't have the GRH. Nevertheless, despite the fact that we don't have the GRH, Linux showed rather amazingly that the least prime in any primitive progression is still polynomial in Q without GRH. So it's most bounds in prime number theory do not have polynomial bounds in them, but this one does. So that's remarkable. Yeah. So the usual proofs you deploy the entire battalion of analytic number theory firepower. Yeah. So L functions and zero density theorems and yeah, you have to you have to worry about whether Siegel zeros exist or not. And yeah, you can do it. Okay, it's like one whole chapter of Ivanich Kowalski. It can be done. But there's a proof which is primarily additive combinatorial in nature, and it's a very recent result here. So okay, but so I won't give the whole proof, but so there are some tricks. Yeah, so you can use sieve theory to replace. So instead of counting least prime in the arithmetic progression, it's enough to count the least product of two primes or product of three primes. So this is cheating quite a lot, but go back to this picture here. You can almost, in some cases, you can define almost prime a bit more precisely as basically primes and semi-primes. The product either one prime or two primes. That's a lie in many ways, but and they both somehow have density 1/2 if you do it correct. And so understanding this set is actually very close to understanding the complement of the set inside that set of almost prime. So there is this sort of principle that in certain cases, asking questions about primes is almost the same as asking questions about positive two primes, because they're complements of each other relative to a much better answered set. And using something called the Bombieri sieve, you can also relate product of two primes to product of three primes, and so forth. So, all right. This only works for certain specific problems. But in particular, it works for the leading problem. Okay, so if you use something called the Bombieri sieve, you can replace, say, products of primes, and say products of three primes. And so you can ask, what is the least product of three primes in an arithmetic progression? That turns out to be morally an equivalent problem, modulo some sieve theoretic values. Okay, so now basically, so this makes it more of an additive combinatorial question. So, so instead of trying to find a prime in a given residue class A mod Q, so maybe the primes live in some other residue classes B mod Q. Okay? So you let A be the set of all residue classes that contain a prime of polynomial size. So if you can, that's some subset of the primitive residue classes C mod QZ. If you can show that A times A times A means little a, then little a mod Q is the product of three primes of polynomial size. So so rather than show that A contains big A contains little a, you need to show that A times A times A contains little a. So that's something that additive combinatorialists are much more happy with. Also, sieve theory will tell yeah, so you can bound the prime by the almost primes twice as big. And so one consequence of that and some visual thing is that you can get a lower bound of the density of A. So A should have density 1. It should fill out all the residue classes. That's what we're trying to prove, basically. But what's easy to show is it has density at least 1/2. Not 1/2 minus an epsilon. Okay. So we have a set of density at least 1/2 in this group, and we want to show that the product A times A times A contains everything. Okay. So this is now a very familiar territory. Okay. Yeah, the problem is that this is minus little o of 1, which is unfortunately a problem. Yeah, so you may know that if you have density bigger than 1/2, then even A times A would actually fill out the whole space. But we have density a little bit less than 1/2. But we know there's an inverse theorem, and it's not hard, that tells you exactly what goes wrong. If you have any finite abelian group and a set of density 1/2 minus an epsilon, and an element A, then either A times A will contain little a, or A is trapped in an index 2 subgroup, actually a coset of index 2 subgroup. This is basically the only bad case. And furthermore, actually, it has to be the coset that doesn't contain A. So that's not high. Yeah, so this is like an easy Fourier analytic proof. In fact, so basically, this solves the problem. This solves Linux theorem unless the set A is trapped in a coset. Now you have to unpack what that means. Okay, so this group is the primitive residue classes of some cyclic group. Cosets come from quadratic Dirichlet characters. Okay, so I just realized I didn't. Well, okay, so the next few slides you need some additive number theory to follow. But basically, the only bad case is if there is a certain Dirichlet character, so that's a multiplicative function on the periodic natural on the natural numbers, which is quadratic, so it only takes values plus or minus one, it squares to one, and it always avoids the value. So chi of p always avoids the value of chi of a for every prime, or almost all primes of size, polynomial size. So basically, the only thing that can go wrong is a conspiracy that that all the primes decide to live in one of the two level sets. So like, think of this Dirichlet character as two coloring the natural numbers, and 99% of the primes are decided to live in one color class, and so the wrong color class for what you want. Yeah. So what added conjectural conspiracy is that this is the only enemy. Now, the standard proof of the analytic number theory proof using all the complex analysis, also gets to this point, but after a lot of complex analysis machinery. But it's somehow very transparent if you do it to the analytic oil setting. Yeah, so there's two cases. Either there's a conspiracy where you're always in the plus one color, or you're always in the minus one color. Yeah, so one of these is called a Siegel zero, and the other is called a Siegel pole. Siegel poles have been known not to exist for ages. Siegel zeros, we're still trying to work on that. But yeah, so yeah, so for example, yeah, so there's two bad scenarios remaining. So one is if A is in the minus one color, and all primes are pretty much in the plus one color. That can't happen basically because if A has color minus one, then one of its prime factors has a color minus one as well. That's not quite the proof because there's a bunch of almost alls that have to be taken into account. But that's sort of roughly this you can make this idea more quantitative, and you can get an easy improvement here. Yeah, there's one hard case which corresponds to the Siegel zero case in the standard proof, which is not coincidentally the hardest case to deal with there. So there's another case where A happens to be in the plus one color, but all primes of polynomial size, or almost all primes, have minus one. And there you have to do something. It's a trick which is standard to number theorists, but it's a bit weird if you haven't seen it before. If almost all primes are in the minus one color, you take the convolution of one, the Dirichlet convolution of one and chi, and then that's got very small mean because that's killing almost all the primes. So you reweight the integers to sort of kill all these primes by inserting this weight, and that turns out to improve the sieve. And I think the density, which was less than one half, gets pushed to like a bigger than one half or something. And you can rule things out by more careful sieve theory. Okay, and you need one number theoretic fact, which is a trivial bound on L function. But you really don't need Siegel's theorem. You need very little analytic number theory. I think that is. Yeah, I have one more bit of application, but I think I'm well. Okay, well, I'll take a few minutes on the last thing. So it's a miscellaneous thing, which is a little bit different from the other applications of algebraic control, but just to show that there's so many, the fields are now much more connected than they used to be. So one standard sieving problem is the following: take a set of primes p up to x, and take the numbers up to x, and count how many numbers up to x are co-prime to this collection of primes. So maybe how many numbers are co-prime to all primes which are 1, 1, 4. So you take some set of primes, sieve out all the multiples. There is a random prediction. If the multiples of p behave randomly, it should be the number of survivors should be the original number x times 1 minus 1 over p for every prime that you're sieving out, because every number has a 1 in p can't be divisible by p. And if they're independent, you should get this product. So that is what you should get. And it turns out sometimes you get that bound up to a constant, sometimes you don't. So as long as you have yeah, so there is a conjecture when this happens. Yeah, so as long as you have how does this work? Enough primes you're sieving. Yeah, yeah. So there's a certain condition that in certain ranges, as long as you have enough primes in various given ranges, then the sieve works. Okay, but if you don't have if you have the wrong number of primes, this is a bit confused. Maybe whether this bound is the wrong way around. But, yeah, okay, but yeah, there was some condition on the density of primes, which ensures that the sieve works, and there are examples that show that if you don't have this, the sieve fails. So I won't talk about the proof at all, but except that the main input is an additive combinatorial statement. Yeah, that if you have a set of numbers 1 to n, and they are and they are large in a certain weird logarithmic sense. If a set is dense enough, then any number n can be up to bounded error be represented as the sum of some finite number of elements of the set. So if a set A is large enough, then the set of finite sums kind of fill out a synthetic set. If it fills out, you can get within bounded error of any target. This is the main input needed to solve this specific conjecture. So this is a miscellaneous example of how additive contours is used in number 3. I'll stop.